Hello, ladies and gentlemen. Today we're going to be working on section 2 of the work and energy unit, which is energy. So section 2 focuses on the energy half of the equation. So first slide starts off with a bit of an intro. You says you have no doubt heard about the term kinetic energy, and yes, you have, because we've talked about it in class before. If you remember, kinetic energy is the energy of motion. So what is it? It is the energy of motion. Okay, so anything rolling, vertical or horizontal translation. This is energy. Spelling is horrendous. Energy of motion. Okay, so that's what kinetic energy is. Okay, and then you have potential energy. Potential energy is stored energy. Okay, so potential energy is stored energy, and it can be stored in a number of ways. Okay, if you think about a spring. How do you store energy inside of a spring? You can store the energy in the spring by either A, compressing it. Once you compress it, what is the spring going to do once you release it? It's going to bounce back. And it bounces back with the energy that you put in it by compressing it. Okay, now it wants to release that energy. You can either compress it or you can stretch it out. When you stretch it, it wants to go back to being the normal length. It wants to shorten. So when you let it go, it'll compress itself and shrink itself back down. Okay, so that's one way to do it with a spring. You can also think about it in terms of height, but I'm gonna stop there. We're gonna as we go through the slides, we'll get plenty of examples. Okay, so just know kinetic energy is the energy of motion, and then potential energy is stored energy, and you can store it in a number of ways. Okay, so work, if you remember from the first section, work is force times displacement. Okay, what they're doing here is they're rearranging the equation to give you, they're showing you where the kinetic energy equation comes from. So kinetic energy is the energy of motion, and if something's in motion, then it has to be doing work. So let's look at the work equation. Work is force times displacement. Force, if you remember, F is equal to ma. So that's where this comes from. What they're saying is they're changing F. This is F. This right here is F. They just changed F to ma. And if you remember from the beginning, closer to the beginning of the semester, when we started talking about 1D motion and we got these kinematic equations, this is one of the equations. Vf squared is equal to Vi squared plus 2ax. They're going to plug that in for acceleration. So what they did here was they got the a times delta x. This part right here, let me change colors. They actually solved for this right here. This part right here. So this part they got by itself. After they got it by itself, they substituted it in back into this piece. So this whole part right here, this Vf squared minus Vi squared divided by 2. If you get that here, what they did is they moved this over, they subtract that over, and then divided it by 2 to get that by itself. So that purple box, this comes from solving the equation above for a delta x. And then after you distribute, you get your 1/2 mv squared. This right here is the kinetic energy equation. I'm going to write it shorthand for Ke. Okay, this is the Ke equation. And you've seen it before. But this is how it's derived. This is where it's come from. So this is the work from motion. This is the kinetic energy equation. That's where that comes from. Okay, so 1/2 mv squared. Okay, this is the energy of motion. This first part, this is the energy of motion. Okay, kinetic energy is equal 1/2 times the mass times the velocity of an object squared. And since it's the same thing as work, it's a unit of energy. Okay, so work is in joules, kinetic energy is in joules. Okay, Work is technically the change in kinetic energy, because if you see here, it's final minus initial. So work is the basic final kinetic energy minus your initial kinetic energy. Okay, work is the change in kinetic energy. You can have a positive change, you can have a negative change. But work is your change in kinetic energy. Okay. They have a mini example here for you. 6 kilogram cat runs after a mouse at 10 meters per second. What is the cat's kinetic energy? All they did was plug in the numbers into the kinetic energy equation, 1/2 mv squared. So in this case, the mass is equal to 6. So for the M, you would just plug in 6. 6 would go there. And then for the V, you'd plug in 10. And you'd have to square it. So this would be 10 squared. 10 squared is what? 10 squared is 100. 100 times 6 is 600. And then 600 divided by 2 is 300. And if you look at what they got 300. Okay, so that's where that number comes from. And then they're saying, suppose the above cat accelerated. How much work was done on the cat to produce this change in energy? So this is, you just have to find the new kinetic energy and then subtract it. Okay, so instead of putting in 10, just put in 12. 12 squared is 144, and then you do 144 times 6 divided by 2. Whatever number you get, you'd have to subtract 300 from it, and that'll give you your work. Because remember, work is change in kinetic energy. So you would do your final, which would be the number you get here, minus your initial, which would be the 300. So if you wanted to get that answer, that's where it would come from. So now, let's look at potential energy. Potential energy, again, is stored energy. Okay? It is stored energy that can eventually, maybe, provide motion. Okay? So the definition they give you is energy associated with an object's potential to move due to an interaction with the environment. Okay, so in this case, a book held above the desk. Okay, if the book is being held above the desk, if you drop the book, that potential energy, which in this case we consider that gravitational. So gravitational energy, think about this. This is stored energy. This is the energy from height. Okay, this is energy from height. So the higher something is in the air, the more gravitational potential energy it has, okay? This is energy from, spelling on this mouse is so difficult. Spelling from energy from height. Okay, that's what this is. So the book being held above the desk. You drop the book is going to fall down on its own and convert that gravitational potential energy into kinetic. Okay, so that's where that potential energy for the book is coming from. An arrow ready to be released from the bow. How do you shoot a bow and arrow? You have to pull back the string. Okay, when you pull back the string, that is elastic. Okay, so elastic is, I'm gonna do it down here. I'm running out of space. Elastic is energy from stretching or compressing, okay? This is stretching or compressing, okay? I'm pretty sure I might spell stretching wrong. I'm a numbers guy, not a words guy. Stretching or compressing. Okay, so you can compress a string. You can also stretch a string. Okay, rubber bands. You can stretch rubber bands. Okay, so that's elastic. In the arrow, you have to pull back the string on the arrow. The energy that you've put into the string is what's gonna move the arrow when you let go. Okay, so that's elastic potential energy. Electromagnetic is things like magnets. Potential energy, you can have potential energy stored in those types of energy, like electricity is a potential energy that we can get out. So that's gravitational, then you have elastic, and then you have electromagnetic. For gravitational potential energy, it's the force equation times height, basically. So remember, F is equal to ma. G can also be written as mg. So just know that this first part right here, this is a force. That's F. Okay, it's basically F times h. So potential energy from gravity is just mass times gravitational acceleration times h. Okay, so this is F. More specifically, that's the Fg equation. Okay, so that mass times g part, that's Fg. That's what that is. So Pe is equal to force of gravity, or mg, times h. And again, you end up with a joule. It's a unit of energy, so joule. Okay, so a newton times a length gives you a energy unit. So this would be a joule. If height is equal to 0, it depends on what you're calling 0, because you can have 0 be at different heights depending on the diagram or situation you have it in. But if you don't have any height, you don't have any potential energy. So then you call that 0. Usually we call the floor, the ground floor is what we usually call the 0 level. This is for gravity. Now we have for springs. Okay, remember, you can compress the spring, you can lengthen the spring. Okay, and the potential energy from spring comes from elasticity. Okay, so for elastic potential energy, you use a different equation. Here, potential is for gravity, it's just mgh. For elastic, it's similar to the kinetic energy equation. For the kinetic energy equation, it's 1/2 mv squared, but instead of 1/2 mv squared, we have 1/2 kx squared, where k is your spring constant, and x is how far you either stretched it or compressed it. Okay, so the spring constant depends entirely on the spring. What spring do you have? How thick is the spring? How many curls does it have? When we were doing the cart lab, where I gave you guys those scales, those springs, you can hang weights on it, and it tells you how much force you're putting into something. We had different colored ones, and some springs were stronger than others. So those stronger springs are going to have higher spring constants. Okay, so this spring constant right here, this term right here, this is entirely dependent on what spring you have. Is stiffer is the proper term, okay? So the stiffer the spring, the higher the spring constant, because it takes more force in order to compress a stiff spring. And then x is just how far did you compress it, okay? That number squared is going to be the x. And again, it's going to give you a unit of energy. It's going to be well, actually, they gave it to you. This is technically, instead of times, this is divided by. No. All right. Well, this is potential energy should be joules. Should be the same. Should be the same unit, and it is if you work it out. It should be. That's a constant. It is. It is. Okay. So here's another example. Let's go through one. Let's make sure everything's good. Yeah, everything should be. Yeah. Yeah. We're good. We're good, fellas. We're good. So classroom practice problem. Let's do this one. When a 2 kilogram mass is attached to a vertical spring, the spring is stretched 10 centimeters, such that the mass is 50 centimeters above the table. What is the gravitational potential energy associated with the mass relative to the table? Okay, so be careful with the units. So gravitational, again, is mgh, but everything has to be in SI units. So we right now, mgh, our m is Our M is 2. Our G is 9.81. Now, the last thing we need is the height. The height, it tells us, is 50 centimeters above the table. We need to convert centimeters to meters. So 50 centimeters would be 0.5 meters. Remember, there are 100 centimeters in 1 meter. So 50 centimeters would be half a meter. Okay? So 0.5 is the same thing as 1/2. So now you multiply everything out. Let's do it this way. 2 times half is what? 2 times 1/2 is 1. And then 1 times 9.81 is 9.81. So that's where this number comes from. Okay? That's where this number comes from. And then it says, what is the string's elastic potential energy if the spring constant is 400 Newton over meters? Now we go to the spring equation. Spring equation is 1/2 kx squared. So 1/2 is again 0.5. So we will be doing 0.5 times the spring constant. The spring constant they just gave us is 400 times x squared. X is the stretching distance. It says the spring is stretched 10 centimeters. So if we stretch it 10 centimeters, 10 centimeters is 0.1 meters. So then it's 0.1 squared. So now we do half. 1/2 times 400 is 200. So this part right here is going to give you 200. And then you do 200 times 0.1 squared. And that's going to give you 2. Okay? So this 9.81 comes from this, and 2 comes from this. You plug in your numbers, and that's what you end up getting. And that's for elastic. Okay? So now you know the two types of potential, or the two types of energy. You have kinetic, which is the energy of motion, and you have potential, which is stored energy. Okay? If you look at the potential energy equation for gravity, just know that mg, that is the weight of the object. It's the weight of the object in newtons, and then you just multiply that by the height. So that's another way to remember it. And then the kinetic energy equation and the spring potential energy are similar. For the spring potential, it's just 1/2 kx squared, where k is the spring constant and x is how far you're stretching it. And then the kinetic energy equation is mv squared, 1/2 mv squared, which is the mass times the velocity. And that's it for the kinetic and the potential. And that's the energy section. And now I want to go through the practice. I'm going to go through 2 problems of the energy practice, the one without the key. Okay, I'm going to go through the one that does not have the key. So let's do 1, 2, and 3. Let's do 1, 2, and 3. So what are we looking for in number 1? What is the final destination? Final destination, we were looking for mass. And what are we given? We are given a distance. And that distance we can use, it looks like we can find velocity. So we're given a distance and a time, which we can use to find velocity, and we're given kinetic energy, and we're asked to find mass. So it's obvious to me we're using the kinetic energy equation. So kinetic energy equation is, I'm going to say K for kinetic energy. K is equal to 1/2 mv squared. And if we're looking for m, we need to do some rearranging, okay? I don't have that much space, so I'm going to do it all in one step, okay? I'm going to explain it, but I'm going to do it all in one step. Okay. So we're looking for mass. So first thing I need to get rid of is the 1/2 and the v. Okay. So in order to get rid of the half, I need to multiply by 2. Okay. If I multiply by 2, it'll cancel over here, and I'll have it over here. So I multiply both sides by 2. So now that'll get rid of the half. And then I need to divide by v squared, because I'm multiplying by v, and that'll bring it over to the other side. If I do that all in one step, you end up getting that m, which is the mass, is equal to, if I multiply by 2, now we have 2 times k. Okay, remember this 2 got rid of the half, and then we got to divide by v squared. Okay, so this is to find mass. So let's go back to number 1. It says that he ran 100 meters in 9.85 seconds. So our velocity, remember velocity is displacement divided by time. So velocity is 100 divided by 9.85. This will give you your velocity. Okay. And now we can answer the question. So we want to know, what is Borel's mass? We have everything we need now. Okay, let me erase this because I need that space. We have everything we need to answer the question. So M is equal to, what is the kinetic energy? The kinetic energy is 3.40 times 10 to the 3, which is 3,400. Okay, that's 3,400. So this is 3,400 times 2. Let me put it in brackets just so it's actually easier to note. Okay, so this is 3,400. Let me put that in brackets just so it's easier to see. People might get confused with the dots. 3,400 times 2. And then all of that divided by whatever you get here for the velocity. So 100 divided by 9.85. That's basically, I'm going to round it. I'd rather you not round it, but 100 divided, this is basically 100 divided by 10. If I do 100 divided by 10, you get about 10. Okay. This is going to give you a number that's a little bigger than 10. So let's say our velocity is 10 for the sake of just rounding and making the numbers easier. Okay, this is about 10. 10 times 10 is 100. So this would be 3,400 times 2 divided by 100. Okay, plug these numbers into your calculator and you get your answer for number 1. Okay, first thing you needed to do was rearrange this equation, the kinetic energy equation, 1/2 mv squared, to get mass by itself, because that's what you're looking for. Okay, after you get that, you just got to plug in the numbers. They give you K. They say kinetic energy is this. That number is 3,400. And then from there, you also need to figure out velocity. They give you distance and they give you time. With that, you can find velocity. So the only little hiccup in here was you had to rearrange the equation and you also had to find or calculate the velocity. It wasn't just given to you. Okay, but that's, you guys know how to do that. Okay, so let's do number 2. I'm gonna leave the mass equation up just because I'm pretty sure we're gonna get asked to do it again some point. And yeah, number 2 is, in number 2 you're looking for mass again. Number 2, you were looking for mass. Okay, and number 2, again, first thing, you just look at the final destination. What is the mass? We're given, okay, they give you everything. They give you everything you need. Straight up. So this is an easier one. Mass is equal to 2 times the kinetic energy. So again, it's a 2 here. They give you the kinetic energy. It's 432 times 10 to the 5th. Okay. So if you're wondering how I'm getting these numbers, again, that the power tells you how many times you're moving the decimal. So this is 5, so we need to move the decimal to the right 5 times. So it's 1, 2, we have 3 more, so you're going to end up adding 3 zeros. Okay? So this is 432,000. That's what that is. That's going to end up being 432,000. So that's 2 times 432,000 divided by the velocity that they give you, which is 23, but you need to square that. Okay, it's 23 squared. Okay, I know it's a little sloppy, my apologies, but plug those numbers in and you will get your answer. So this is 2 times 432,000 divided by 23 squared. Okay. So remember 10 to the 5th, that's 1, 2, and then you have 3 more to go. You just add 3 zeros. So that's number 2. You got the equation, just plug the numbers in, you get a number. You plug your numbers in, you get the answer. I want to leave the mass equation up in case the X is to find it again. So that was 2 mass ones. I want to do one that isn't mass. Is there anything with velocity or speed? Okay, so in this case we're looking. Okay, let's do number 5, because number 5 they're asking us for something different. Number 5 they're asking us for speed. Speed is the velocity. So now we have to solve for velocity. So remember the kinetic energy equation is originally 1/2 mv squared. Okay, so ignore what's over here for now. I'm gonna use this to solve. Ignore that. Okay, so K is equal to 1/2 mv squared. To get v by itself, they actually solve it for. They had the equations right here. You can see where it comes from. You multiply both sides by 2, that's where the 2 comes from, to get the 1/2 to get the 1/2 away. Then you got to divide by m. You got to divide by m, and that's how you get the v squared by itself. And then you need to take the square root to get your v finally by itself. So they moved this over by multiplying by 2. They moved the m over by dividing by m. That's how you get 2 times ke divided by m. And then to get rid of the square, you have to take the square root. So this equation right here is the equation we're going to be using. It's v is equal to 2 times the kinetic energy divided by mass. And then take the square root of that whole thing. This is the equation we need to do number 5. Okay. So in number 5, what are we given? We're given the mass, and we're given the kinetic energy, and we're just asked what is your speed going to be. So they give you everything. They give you everything you need. Okay. They give you everything you need. It's just a matter of plugging in the numbers. So for number 5, it's just v is equal to, I'm going to do the square root at the end. No, I'll just do it now just to see how much space I have. So it's the square root of 2 times 2 times the kinetic energy, which is, we're adding 2 zeros, 900 or 99,600. So 99600, we're adding 2 zeros. And then that divided by the mass, and the mass was 51 kilograms. And then this again, this equation right here, 2 times ke divided by m. You plug those numbers in, and you will get your answer for number 5. Okay? So you can get asked to find 3 things. You can either get asked to find mass, you can get asked to find kinetic energy, or you can get asked to find velocity. If you are asked to find velocity, this is the equation you're using. Okay, I'm going to set up the equations for you. If you're asked to find velocity, this is what you're looking for. If you're asked to find kinetic energy or change in kinetic energy, this is the equation you use. And if you're asked to find mass, we solved for mass already, but if you're asked to find mass, this is the mass equation, okay? It's 2 times Ke divided by V squared, okay? So this is the mass equation, this is the velocity equation, this is the kinetic energy equation. They're technically all the same equation because they all come from each other. They're just rearranged versions of each other. So they're all technically the same equation. But just these are, if you're looking for mass, use this one. Kinetic energy, use this one. Velocity, use this one. Okay, those are all the tools you need in order to get through the sheet. Okay, if you have any questions, again, always feel free to ask, and I will do my best to give you the best explanation possible. Take care.